Hi all, I welcome you all to the next lecture today, Thermodynamic Relations, Volume 2. In the previous lecture, we have seen the relationship for Maxwell equation and also the relationship for two TDS equation been derived in the previous lecture, and parallelly you have seen the difference between specific heat at constant pressure and specific heat at constant volume, and we have expressed those Cp minus Cv in terms of the coefficient of coefficient of expansivity and coefficient of compressibility. So today we will start the discussion from both the TDS relations. We will try to develop expression for the enthalpy, internal energy, and other properties, right, in terms of basic fundamental properties, pressure, volume, and temperature. Let's start our discussion for today. So this is the question. Basically, this is derivation which says that you have to relate TDS relation in terms of the coefficient of expansivity and compressibility, right? And as well as there is a relationship where you have to relate Cp and Cv in terms of Cp and Cv, including coefficient of compressibility and coefficient of expansivity. So how to do that? So we know that volume expansivity beta is given by 1 by V dou V by dou T at pressure constant, and isothermal compressibility is nothing but minus dou V by V and dou P at constant temperature. So these are the basic two coefficients being expressed to you in the previous lecture. Now what you need to do, basically you have to develop an expression, right, by connecting two TDS equations. One is for open system, one is for closed system, and by combining and doing the rearrangement of terms, you have to express the TDS equation in these three different forms. So from first TDS equation, we know that TDS is equal to Cv dt plus T dou P by dou T at constant volume and dV, right. This is the first TDS equation, and we also know that beta by K, if you divide these two terms, right, you can write in this way: dou V by dou T at constant pressure divided by dou V by dou P at constant temperature, which can further be rearranged in the following term, right, following way, right. You can write dou V by dou T at constant pressure multiply by dou P by dou V at constant temperature. Now you know fundamental relation between properties pressure, volume, temperature, right. Partial derivatives, they are basically connected via this equation, right. Dou V by dou T into dou T by dou P, and dou P by dou V is equal to -1. So I need the value of these two terms, right, basically, which are given here. So if I look for these two terms, I will find these terms here, right. One term is here, that is dou P by dou V, and T I can get from here, and dou V by dou T is given here. These two values I need out of this equation. So I can write from here minus dou V by dou T P, and this is equal to dou P by dou T at B. So look at this term. What is this term basically which is present here? Look at which is present here, which is nothing but beta by K, right. Already we know. So the first expression, right, you look at here, already we have got it. So Cv dt plus T, and this term what you are writing, this one, these include these two terms already present by beta by K. If you substitute this value, you can get this expression. So first expression is over. Now you have to go for the second expression, right. So second is the second TDS equation you have to use. This is the first TDS equation. Now second TDS equation, when you have to express in terms of this volume expansivity. So first term is okay, you can substitute and you can prove it. Now go for second TDS equation, which is this. Now I need the value of this, right. So the volume expansivity is given by this term, right. So only I need this term. This term is nothing but beta into V. If I substitute this value here back, right, I can get the second expression, right, which was desired, right, Cp dP into 2 and dP. So this is very simple. You can substitute this value out here and you can get this expression. Now last expression where we wanted to have both Cp and Cv in a single term along with those two coefficients. So we will go with the basic definition of entropy. Entropy is a function of pressure and volume. So we can write the differential form of it. ds is equal to dou s by dou p into v into dp and this term. So this differential change in entropy can be written this way. And if we multiply both side by t, because we need to write t into ds, so we multiply both side by t, we can write this expression, right? This expression. Now look at this term basically. This is dou S by dou P, right, at V, and already we know that entropy is also function of temperature and what we say pressure. So this term can be divided into two terms, right? Dou S by dou T into dou T by dou P. Anyway, this and this will cancel out. You will get only dou S by dou P. So this term has been divided into two partial derivatives, right? Dou S by dou T into dou T by dou P at constant volume. Same treatment can be done for this as well, because entropy entirely, the function of temperature. So it depends on temperature. So temperature is also there. So temperature dou S dou T you have added. This term also got divided into two terms right here. Now separately you can write these two terms, right? This separate volume and this volume, and similarly these two terms can be taken out from here. Now what you need to do, you know the basic definition of Cp. So Cp is nothing but T into dou S by dou T at P, and similarly Cv is equal to T into dou S by dou T into B. From where you are getting this? For constant volume process, heat transfer is equal to change in internal energy, Cv dt, right? And heat transfer for reversible process is equal to T into ds. Similarly, for heat transfer for constant pressure process is nothing but Q is equal to Cp dt, right? The same thing is here. From there you have written the Cp and Cv expressions. So TDS equation, right? Whatever you got here, right? Got here. These terms can be can be replaced by Cp, right? The Cp and Cv. So if substitute the value of this, you can write TDS equal to Cv dou T by dou P, because this term is already there. You look at here this equation. So you are replacing only this term, right, and this term here. This term with Cp, and this complete term with Cv, and these terms parallelly will be left with. So you have written here. Now from beta by k, this is dou p by dou t at b, and opposite of this can be written as dou t by dou p at b, and this term is already available here. All right, this term is already available here, and one term is here, right? So these two forms can be added here. So you can write TDS is equal to Cv, and this term is nothing but k by beta. So this as you have put here, and dp plus Cp, and this term is nothing but dou t by dou v, right? Dou t by dou v, same to same you can write here at p into dv. So this is the another expression. So now volume expansivity is written. Now next term we need to look for this. So volume expansivity is 1 by V dou V by dou T at P. Look at this term. This term value can be kept over here. So dou T by dou V at a V at constant pressure is 1 divided by beta B. And now you substitute this value over here. You will get the third equation, right? So TDS equal to Cv K dP by beta plus Cp beta B into dV. So this is the final expression, that third expression, right, which was desired. So you have got that. So like that you can make the arrangement of TDS equation in three different forms. Now go for equation of internal energy and enthalpy, right? These are very important derivation. So let internal energy for a closed system, we know that it is a function of temperature and volume, because volume is fixed. So U is a function of temperature and specific volume. So change in U can be written as dou U by dou T at constant volume dt plus dou U by dou V at constant temperature dV. Right. Now look at this term, right? Basically, what is this term mean? This term is nothing but your Cv, right? Because du is equal to Cv dt. So dou U is equal to dou U by dou T can be written as Cv, right? So in place of this term, you can write Cv. So Cv dt plus dou U by dou Vt dV. To evaluate this term now, you need to make another assumption that entropy, internal energy is a function of entropy and specific volume, right? Specific volume. So then you can write change in du is equal to dou u by dou s at volume ds plus dou u by dou v at s dv. Why I am considering entropy again? Because whenever you are supplying anything to a closed system, that will basically increase the randomness of the system. Whenever there is a randomness in the system, that is directly due to the entropy, right? So entropy term need also be considered importantly, like temperature. So U is a function of entropy and volume. So second expression you got from here. Now from this, right, basically this term as I said, U is a function of S and V, right? So this term can further be written as dou u by dou V at t is equal to dou u by dou S at V into dou S by dou V at t plus dou u by dou V at S, right? You can write this term. What you have done exactly, you have differentiated you divided this complete equation by dt, means dou v, right? So you are getting dou u by dou v at a constant temperature is equal to first term and dou s by dou v at t plus this term, right? And this dB by dB will be cancel out, so dV term is vanished here. But you already know from the heat transfer, right? For a closed system, heat transfer is equal to change in internal energy. So T into ds is equal to du. So this term already you know, dou u by dou s is equal to T, right? Or you can say dou u is equal to T into ds for constant volume process, right? This term can be replaced by temperature, right? Also, you look at this dou s by dou v at T, right? Can be written as dou s by dou t at v, right? And dou u by dou v is equal to minus p. So if you differentiate internal energy, right, with respect to volume, that is nothing but equal to minus p. So if you substitute this value over here, right, in this equation, this is the basic equation that you got. So if you substitute the value of all these terms, right, in this equation, you can write dou u by dou v at t is equal to, this term is t, right, and this term is equal to basically dou p by dou t at b, and this term, right, dou u by dou v is nothing but minus p. So this is the first equation that is known as energy equation. Energy equation. If you write these values over here, right, if you substitute this complete value out from here and substitute over here, right, by keeping in mind these all terms, right, minus p and minus p, if you substitute this all value, du can be expressed in terms of cv dt plus this additional term, right, that will come over here. Alright, so you can express in this way. So du is equal to cv dt plus bracket t dou p by dou t at b minus p dv. So to evaluate change in enthalpy, again you have to make the analogy. Enthalpy is a function of temperature and pressure, right? So dh can be written as dou h by dou t at p dt plus dou h by dou p at t dp, right? Now this term is what, basically this is nothing but heat transfer, right? Cp dt, right, is a heat transfer. So Cp dt, we can in place of this we can write Cp into dt plus this term we need to evaluate. Again enthalpy, whatever you are supplying something will be a function of entropy, right, because temperature already you consider. Now enthalpy is a function of entropy and pressure, right? But in the case of closed system it was the entropy and volume. So now you can find out the change in enthalpy. dh is equal to dou h by dou s p ds plus dou h by dou p s dp, right? Now we need to find out basically dou h by dou p at t, right? So we have to divide this entire equation by pressure, right? So we can write dou h by dou p at t is equal to dou h by dou s at p into this term. This term why coming, because this ds by dp, right, because we are dividing by dp throughout, this dp term will vanish. So we can write this equation, right? This term, if you look at, this term is equal to temperature, right, because dh is equal to t into ds. So this become t, right, this complete term is t, and this using the Maxwell relation, basically we are writing dou s by dou p t is equal to minus dou v by dou p at p, and last term dou h by dou p, if you do that, that will be equal to v, basically, because h is equal to u plus pv. If you write pressure will be differentiated, you will get only v, and internal energy cannot be differentiated with respect to pressure, right? Cannot be cannot be differentiated. So you can write h is equal to u plus pv, right? So if you differentiate dou h by dou p, first term is 0, and p into v differentiation will give only v. So you got v. If you substitute all these values, right, out here, you can write dou h by dou p is equal to v minus t dou p by dou t into p. Now you substitute back this equation into Dh equation, you can write Cp dt plus this bracket V minus T dou Vy dou T P into dP. So this was the second equation based on the energy concept. So you have derived the expression basically for internal energy as well as enthalpy change, right? Again, I am repeating the things because you should not get any doubt in this. So here equation for internal energy, how actually you derived? For a closed system, we know that volume is a fixed, right? So we can say internal energy is equal to a function of temperature and volume basically. So you can write du, right? Very differential form. And first term du is equal to T into ds, right? With I already know T into Cv, because change in internal energy is equal to Cv dt. So dou u by dou t becomes Cv. You substitute here. This value is unknown that need to be calculated. So second assumption we have made, u is a function of entropy and a specific volume. So we can write du is equal to dou u by dou s b ds plus dou u by dou v as dv. Right now you divide throughout by volume because I need this term, right? Dou u by dou v. So divide throughout by dou v. So this term is as it is, and this become dou s by dou v at t plus dou u by dou s. Right? This as it is, and dv cancel out. I got this. Now this first term you look at dou u is nothing but change in internal energy for a closed system is equal to T into ds, right? So this dou u by dou s became T, and this term using the Maxwell relationship, right? Maxwell relationship, I can write dou s by dou v at T is equal to dou s by dou T at V, and last term this one. So internal energy is can be written as P into dV, right? Basically dq is equal to du plus P dV. So du is equal to minus P into V, right? Minus P into V. If you differentiate u with respect to V, right, you can get only minus P, because du is equal to minus P into V, right? So minus P into V, if you differentiate with respect to the volume, you will get only minus P. So this is the minus P, right, which you got. Now substitute all these values back here, you can get dou u by dou v at T is equal to T into dou P by dou T at B minus P. So this is the value of dou u by dou v at T. So you need to put this value back over here to get the change in internal energy. So dou u is equal to this term. So this is the one equation, right? Change in internal energy equation. If further integrate it, you will get the net change in entropy between the given points, right? Given temperature ranges, you can find out the change in internal energy. Similar treatment we have done for enthalpy. So specific enthalpy is a function of temperature and pressure. So dH can be written in this way, right? Once you know the dH, this term is what? Basically this is a heat transfer, right? dH is equal to Cp dt. So this dividation, this dou h by dou t becomes Cp and dt. Now this value is unknown. So second again we made a function h is equal to function of entropy and pressure. So we have written based on this one equation over here. Now look at this term. This is nothing but dou h is equal to T into ds, right? Because dou h represents the heat transfer in a constant pressure process. So this becomes T, and right, and this term basically we will find out by using the Maxwell differentiating the h. So divide throughout by what you need, pressure, right? So divide this complete equation by dP, right? So if you do so, you can get this term. Now the first term already I said this is a temperature, and using the Maxwell relationship I can relate this also in terms of common properties, and this term h is equal to u plus pb. If you write h is equal to u plus pb, if you differentiate that equation with respect to pressure, you can write dou h by dou p is equal to just volume. So these all terms you can get. This is Maxwell relation, right? This is a fundamental dou h equal to TDS, and this is V. If you substitute back, you can get dou h by dou pt this value, and substitute this back to the first equation, right? You can get dH. This is the enthalpy relation. So dH is equal to Cp dt plus bracket V minus P dou V by dou T at P Tp. So this is regarding the enthalpy relation. Right. So for today this much is enough. I think so. I am not going to teach more. So today we have basically derived total 4 derivation. First we have expressed the TDS relationship in terms of Cv and 2 coefficients, right? volume expansivity and isothermal compressibility. And further, we have also expressed the second TDS relationship in terms of Cp and both of these coefficient. And a final expression, we have expressed TDS equation in terms of Cp/Cv as well as the coefficient of expansivity and compressibility. And then later on we derived the expression for internal energy, right, change in internal energy and enthalpy. So these are the basic 5 derivations which we have covered for today, right? So just go through this for today discussion. This much is enough. If you have any doubt in this, feel free to write in the comment section, right, or you can directly approach to me my WhatsApp number. See you all in the next class. Have a nice day. Good day.